video, we are going to look at exothermic and endothermic reactions. So what are they? How are they different? What about their energy levels? In the next couple of minutes, you'll know everything you need to get started. An exothermic reaction gives off energy to the surroundings, like this fire giving off heat, whereas an endothermic reaction takes in energy from its surroundings, like this poor melting snowman taking in the heat. Just remember, exo means external, so giving out, and endo means internal, so taking in. Let's start by having a quick look. Because exothermic reactions transfer energy to the surroundings, and this energy is usually heat energy, they cause the surroundings to heat up, just like a bonfire, keeping everyone warm. Other examples of exothermic reactions are the neutralization reactions between acids and alkalis, the reactions between water and calcium oxide, and respiration. It is easy to detect exothermic reactions. Just get your thermometer and see if the temperature increases. Watch the hydrochloric acid and sodium hydroxide solution being mixed and see how the thermometer increases. Most chemical reactions are exothermic because heat is given out. Physical processes can also be endothermic or exothermic. When something freezes, it goes from liquid to solid. Bonds need to be made for this to happen, and to make bonds, you need to do some work. Thus, energy is given out and freezing is exothermic. Similarly, when condensation happens, because a gas is going to liquid, again, bonds need to be made, and so energy is given out. So freezing and condensation are both exothermic. Because in exothermic reactions, energy is given out to the surroundings. This means that energy of the reactants is higher, and the energy of the products, hence the energy curve for the exothermic reactions, will look like this.
So this is what an exothermic reaction path diagram looks like, but I'm just going to take a moment to elaborate a bit more. First of all, the name of this graph is called a reaction path or a potential energy diagram, and that's because we have potential energy plotted here on the y-axis, and you have the direction of the reaction occurring on the x-axis. So yes, we do have our reactants on the left-hand side, and they have a certain amount of potential energy. And then it shows the products here on the right-hand side, and they have a certain amount of potential energy. And the really key thing about an exothermic reactions, as I said in the video, is that products have less energy than the reactants, meaning from start to finish, the reaction is losing energy. It's giving that energy off. It's releasing that energy, or XO you can think of as the word exit. Energy is exiting the system, or the reaction as we call it. There's just a few more things that I want to point out here, and I would like for you to label that as well on your note sheet. The first thing is the top of this hill. Okay, notice that the reactants start off with some amount of energy, but then they have to gain energy. And the top of this hill, the maximum point on this curve, please label that as activated complex. This is also called the transition state. This is where the reactants, they start to rearrange the atoms and they start to turn into those products. And you're going to get this in-between state between the reactants and the products. So notice here that the reactants have to gain potential energy in order to reach that activated complex and to start turning into those products. So there's a certain quantity of energy that all of our reactions have to gain in order to start. And this quantity of energy, as I labeled here, is called the activation energy. Please make sure you have recorded, okay, and labeled activation energy on your graph. And the way that we find activation energy is, as they've shown here, is it's the distance between the top of our graph, that activated complex, and the reactants. Okay, so sometimes you're going to see it drawn this way, and other times I like to draw a dashed line like so. Oops, let's line it up with the other one. You can certainly draw activation energy as they've done there. Other times you're going to see it like this. They all mean the same thing. Okay, so this is your activation energy, the distance between the activated complex and the amount of energy that the reactants have. And so we give activation energy this symbol. It is EA, a capital E, lowercase a, capital E for energy, lowercase a for activation. And so we're going to actually have to calculate this sometimes by looking at this graph, and the way that you calculate it is that activation energy is equal to the activated complex, which I'm going to abbreviate AC, minus the reactants. Okay, so if you're asked to calculate the value of the activation energy, EA, you take the value of the activated complex and you subtract the value of the reactants, and you'll have calculated the amount of energy needed to start this reaction, to activate it. Another thing that I want to point out on this reaction path diagram is the amount of energy released, and pointing out how we can determine the quantity of that energy by reading one of these diagrams. So they've labeled here the energy released, and they are exactly right. It is the difference between where the products are and where the reactants are. In other words, how much energy the products have minus the amount of energy that the reactants have. And so I'm just going to clarify a bit more. If I was trying to find the amount of potential energy of those products, I would go to that product line, and then I would run my eyes over here to the y-axis, and I would be able to read, if this had numbers on it, the amount of potential energy that the products have. And I can see here that the difference in energy of those products and reactants is represented in this area here, where they've drawn this orange arrow and labeled it energy released. So if you're asked to calculate the amount of energy released, okay, we can do that. We're going to follow this formula. Okay, the amount of energy released is going to be equal to the products minus the reactants. Products minus reactants. And so we're going to give this a fancy name. We'll call it delta H, or the change in enthalpy. And that is equal to the products minus the reactants. And I'm just going to abbreviate here, P minus R. And that's going to give us that distance between the products and the reactants, which is, in technical terms, this value called delta H, or a change in enthalpy. Okay, so delta H is that change in enthalpy. And in our terms, we can just think of enthalpy as heat. And you can see here in this exothermic reaction, the products have less energy than the reactants. And so when I calculate this products minus reactants, I'm going to get a negative answer, because the products have less energy than the reactants. So mathematically, we are going to end up with a negative answer. So big picture here, guys, we want to see that an exothermic reaction has an energy path diagram in which the products have less energy than the reactants. And the difference between the products and reactants is called the change in enthalpy, or delta H. And then one more thing is to note that the amount of energy needed to start the reaction, called the activation energy, is going to be found by taking the activated complex at the top of the graph and subtracting the value of your reactants.
Now let's have a look at endothermic reactions. These are less common. Remember that endothermic reactions take in energy from the surroundings. Again, as with exothermic reactions, the energy being transferred is usually heat. So in endothermic reactions, the surroundings usually get colder. Again, we can detect endothermic reactions with a thermometer because the temperature would get colder. Some examples of endothermic reactions are electrolysis, the reaction between sodium carbonate and ethanoic acid, and photosynthesis. Endothermic reactions can also be seen in physical processes. When something melts, it goes from a solid to a liquid. For this to happen, bonds need to be broken. And to break bonds, energy needs to be put in, like our melting snowman. Boiling is also endothermic because energy needs to be put in to break the bonds for the liquid to turn to gas. Because in endothermic reactions energy is added to the reaction, the energy of the products is higher than the energy of the reactants. And so the energy curve looks like this. So there you have exothermic and endothermic reactions. All you need to remember is that exothermic reactions give out energy and endothermic reactions take in energy. Both can be detected with a thermometer. In exothermic reactions, the surroundings get hotter, and in endothermic reactions, the surroundings get colder. Exothermic reactions start with more energy and end with less, while endothermic reactions start with less energy and end with more.
So we have the difference here in our exothermic and endothermic energy path diagrams. You should be able to look at an energy path diagram and right away know if it is exothermic or endothermic. And it's all about, guys, where the products are in relation to the reactants. So we're just going to highlight again some key points here. That difference between our products and our reactants, that's the delta H. That's the change in enthalpy. It is equal to the products minus the reactants. So take a look here. In an exothermic reaction, the value of the products is lower than the value of the reactants. So when all of our exothermic reactions, we're going to get a negative answer for delta H. Okay, it's going to have a negative value. And then also, if we were to write out the balanced chemical equation for our reaction, and we'll just write it generically, reactants, then we'll draw an arrow and say they turn into the products. Okay, so we have our reactants turning into our products. These would actually be replaced with the real chemical symbols for that particular reaction, but we'll just leave it very generic, reactants and products here. Now my last part, to turn this into a thermochemical equation, remember that thermo meaning heat, or more generically energy, we're going to add energy to one side of our arrow. And so just take a look at the potential energy diagram. Which side has less energy? That's going to be the product. So to even this out, because we know energy has to be conserved, to even out our reaction, we're going to have energy written on the product side of our balance equation because the products have less energy, so we're going to have to write the energy with the products here. And the way that we measure energy, it's going to be written usually in kilojoules, and joules being a unit for energy. Now, if I take a look at the endothermic reaction, notice the difference in shape. We still have reactants on the left. We still have products on the right. We still have that activated complex at the top of our graph. Activation energy is still the difference between the activated complex and down to the reactants. And that delta H is still the products minus the reactants. But now for an endothermic reaction, since the value of the potential energy of the products is going to be greater than that of the reactants, when I actually do the math, products minus reactants, we're going to get a positive value. Okay, that's going to be some amount of positive number of kilojoules. And I'm going to do the same thing. We're going to write out a thermochemical equation. We have reactants turning into products. And to make this a thermochemical equation, let's write the word energy on one side of the equation. Now look at your potential energy diagram for an endothermic reaction. Which side, okay, has less energy, and meaning which side should we add the energy to? That's going to be the reactant side. So we're going to add the word energy to the reactant side. And remember, you're either going to see the word energy or you're going to see a number with the unit of kilojoules after it. Okay, so bottom line here, guys, take home message. Know the difference in an exothermic and an endothermic energy path diagram. The parts are the same. You always have reactants on the left, products on the right, the activated complex at the top. Activation energy, the difference between activated complex and the reactants. Delta H is always products minus reactants, but there's a difference here. Exothermic is going to give me a negative value of delta H. Endothermic is going to give me a positive value for delta H. And then when we're looking at the balance equation, the placement of the word energy or the value of kilojoules is going to go on the side of the equation that has less potential energy. So for example, exothermic, since the products have less energy, we're going to put the energy with the products, okay, to balance it out. And then for an endothermic, since the reactants have less energy, we're going to put the energy on the reactant side to balance out the amount of energy that the products have on the other side of the reaction. So make sure in your notes you have the thermochemical equations written with energy on the appropriate side of the arrow. And you also know that delta H is products minus reactants. And for exothermic, it's going to give you a negative delta H. Endothermic, it's going to be positive.
Freezing and condensation are exothermic because bonds need to be made, which gives out energy. Melting and boiling are endothermic because bonds are broken, which requires additional energy. Think of the snowman again. And finally, exothermic reactions are more common.